In this video, we are going to be looking at something quite extraordinary. It is the problem of finding an orthogonal diagonalization of a matrix with a specific matrix that looks quite pretty. So the matrix we're going to work with is the following: 0, 1, 0, 1, 1, 0, 1, 0, 0, 1, 0, 1, 1, 0, 1, 0. And we can notice here that this matrix is symmetric. No wonder, because the symmetric matrices are the only matrices that can be diagonalized orthogonally. What does that mean? Well, usual diagonalization says that we need to present this product to be a diagonal matrix, which is the same as, so just a remark here, of course this is the same as saying that the D is equal to what am I talking about here? Sorry. I wanted to say I think it's the same as having A equal P D P inverse. You just multiply the left hand side by P, the right hand side by P inverse to move from the left equality to the right equality, and do the reverse for moving from the right equality to the left equality. Okay, so it doesn't matter which equality we're going to work with, so we're going to work with this one. And now the question of orthogonal diagonalization is where we require this matrix P, which is supposed to be an invertible matrix, since we've got an inverse there, to be an orthogonal matrix. An orthogonal matrix is a special kind of an invertible matrix. You see, in an invertible matrix, you've got the columns to be linearly independent. In an orthogonal matrix, not only are the columns linearly independent, different columns are orthogonal to each other as vectors. The angle between them is 90 degrees. And moreover, also, the length of each vector, of each column vector, in other words, the norm of that vector, is 1. We say that the columns form an orthonormal sequence. And a fascinating fact about orthogonal matrices is that these are exactly those matrices whose inverse is equal to its transpose. So when we are asking for an orthogonal diagonalization, another way of writing down this equality is to write it this way. Of course, with the remark that P must be an orthogonal matrix. That remark applies here as well. And in both cases, we do want definitely that D is a diagonal matrix. Okay, so we've just clarified what it means to have an orthogonal diagonalization. Now there is a fascinating fact in mathematics that the matrices that have orthogonal diagonalization are exactly the symmetric matrices. Can you believe that? So if a matrix allows such a decomposition, in other words, the decomposition we wrote earlier where we had A equals blah blah blah, which is equivalent to these, with the P being an orthogonal matrix, then such A must be symmetric, and the other way around. If it is symmetric, it will always allow such decomposition. Now going back to the A we've got here, it is symmetric, right? How do I tell that it's symmetric? Well, I need to draw in the diagonal, and then I need to see if the entries of the matrix are reflections of each other on the left of the diagonal relative to the right of the diagonal. And you can see that they are. Somehow our brain is good at recognizing symmetry, right? Great, so the matrix A is symmetric. That means that the matrix A will definitely be orthogonally diagonalizable. But now how do we find the orthogonal diagonalization? In other words, how do we find the P matrix and the D matrix? Well, as it is the case with the general diagonalization problem, to find diagonalization, we need to find eigenvalues and eigenvectors. And then we arrange the eigenvalues as the diagonal entries of the diagonal matrix, and the corresponding eigenvectors in the same sequence, we arrange them as the columns of the matrix P. With orthogonal so let's just make another remark here, that since we want P to be an invertible matrix, we want to select the eigenvectors in such a way that they're linearly independent from each other. So those columns, those eigenvectors rather, that will appear as columns of the matrix P have to be linearly independent of each other. Otherwise, the matrix P will not be invertible, and the other way around. So it's necessary and sufficient for invertibility of that matrix to have its columns linearly independent. Okay, so diagonalizing matrix means finding linearly independent eigenvectors, but now orthogonally diagonalizing means finding an orthonormal sequence of eigenvectors. Eigenvectors which are not only linearly independent from each other, but also which make up an angle of 90 degrees between any two of them, and each of whose norm is equal to 1. Okay, so let's get on this very exciting journey and see how to do all of that. Well, the first step in the journey has nothing to do with orthogonality. The first step is to find the eigenvalues, and that has to do with the characteristic equation. So we want to find, in this case, in this example, what the characteristic equation is. In general, the characteristic equation looks like this. The determinant of a minus lambda I equals 0. In this specific example, that amounts to taking the matrix A we had before and subtracting lambda from its diagonal entries, leaving all the other entries of the matrix the same as was before, because you see we're subtracting from A lambda times I, where the I is the identity matrix, and the effect of that is exactly what I just said. Okay, so minus lambda, minus lambda, minus lambda, minus lambda. The other entries are left the same. There we go. That's the determinant of a minus lambda I. And that has to be equal to 0. But first, let's see what the determinant is. It's a 4x4 matrix, so we better take care in our calculations not to make a mistake. Minus lambda times the determinant of a 3x3 matrix, which is minus lambda, minus lambda, minus lambda there. Then we've got 1, 0, 1, 1, 0, 1. Then we have minus 1 times the determinant of minus lambda. No, sorry, there's no minus lambda there anymore. It's 1, 0, 1. Then we have 1 minus lambda 1. And then we have 0, 1 minus lambda. Okay, next we have plus. We got lucky here, it's a 0. And it doesn't matter what we put in here, it's 0 times that. And then we have minus 1 times the determinant of, so the matrix here we have is 1, 1, 1, minus lambda, 1, 0, 0, 1. Okay, we are now going to look at each of these determinants individually. So that's 1. Then this is the other one. And that's the third one. The first case, we've got minus lambda times the determinant of this 2x2 matrix, which is lambda squared minus 1, right? Then we have minus 1 times 1, because of that 0 there. So in the end, what this gives us is Maybe we just leave it like that for now. Okay, so for the next one, we've got here 1 multiplied by lambda squared minus 1, and minus no, my apologies, I made a mistake somewhere there. Let's go back. Which should be minus 1 times, and now I have to delete the middle column here. So that's going to give us minus lambda minus 0. Okay. For this one, we have 1 times lambda squared minus 1. And then we have minus 1 times minus 1, because 0 times minus lambda is 0, and we get here minus 1. For the third one, we've got 1 times 1 minus lambda, so that's going to be 1 plus lambda, right? Then we have minus lambda multiplied by, that's 0, and then it's another minus and plus, right? By plus lambda. Okay, putting everything together into where it came from, we're going to get the following. So we had here minus lambda. If I look here, we had minus lambda times the determinant, and then the determinant is equal to this, so it's minus lambda times minus lambda. I'm deliberately not factoring things out, not multiplying things out. And then we have here plus lambda, right? And the second term is minus 1 times that determinant there, and so it's going to be lambda squared minus 1 plus 1. And the third one is minus 1 multiplied by this thing here, which is 1 plus lambda plus lambda squared. Right? We do not want to multiply this out. The characteristic equation, by the way, is all of this equated to 0. Why do we not want to multiply this out? Because if we multiply this out, we're going to get a quadratic equation, and we will have no idea how to solve the quadratic equation. But on the other hand, if we don't multiply out anything, there is nothing much we can do to proceed with the simplification and solution of the characteristic equation, because there is no common factor to take out, right? So we have to be clever now in our calculations to decide, in order for us to make the right decision of what to do. Okay, so let's try to be clever. At this point, indeed, nothing factorizes out immediately, except possibly here with lambda squared minus 1. Should we try to factor that out? Let's give that a try. If we do factor that out, we'll have lambda squared minus 1 multiplied by, so here I'm going to keep my, maybe I do multiply that in, so that it will be lambda squared what am I even talking about? We can't even do that. Sorry, we can't factor out lambda squared minus 1, right? So maybe we do want to simplify this a little bit, but not too much. So let's indeed try to multiply this out, but not entirely, even though we will end up doing it entirely. So I was totally wrong what I said before. Scratch that. Okay, let's see. So we'll have lambda squared times lambda squared minus 1 minus lambda squared, right? We could have also taken that lambda out as a common factor, I guess. Maybe that's a clever thing to do. Instead of multiplying out, let's take a factor out. So we'll then have minus lambda squared, and then we'll be left here with minus lambda squared minus 1 plus 1, right? That doesn't seem to help much. What about the second term? Well, in the second term, should we do the computation here? Minus 1 plus 1, should we make it into a 0? Let's give that a try. So they'll have minus lambda squared. Then in the third expression, what are we going to have there? We're going to have there minus 1 minus lambda squared, right? What do we do next? Aha. Maybe what we should do next is to make sure we didn't make a mistake. And in fact, I already made sure of that, and I got convinced that I did. If I go back here, I did something very bad right here. You see, when we were computing this determinant, we have to multiply 1 with the determinant of that thing, which is 1 minus 0 times that. So that term falls away. Then we have minus lambda times the determinant of this thing here, which is minus lambda, which is plus lambda. Okay, so that term is fine. But then we are missing one term here, and we need to have plus 1 times minus 1. So that's going to be plus minus 1. And with this correction, we are going to have, at the end here, we're going to have the 1 and the minus 1 are going to cancel out, and we're going to be left here with plus lambda squared. And putting this back into here, so what we get here is just lambda squared. And we have a lambda squared here as well, because minus 1 and plus 1 give us 0 together. And now we can factor out the lambda squared. So after all, my intuition of factoring out instead of multiplying out wasn't so wrong. One good lesson we learned from this is that if we have to kind of be careful to monitor our calculations, if things are starting to look strange, it might be an indication that we made a mistake somewhere. And in this case, I did make a mistake. I apologize for that. Maybe many of you looking at this video picked that up. Maybe some of you didn't. But in either case, we can now proceed with the solution. So factoring out lambda squared is going to give us lambda squared times. Now let's see what we're going to be left with. So here there was a minus, right? Maybe we keep that minus here, so we factor out minus lambda squared. Then so that minus comes from this minus here, so we don't have to worry about the inside part. So then what we have inside is, if I take the lambda out, I'm going to have 1, and then there is minus lambda squared, and then another 1, right? So it's going to be lambda squared plus 2. It seems so. Okay. So that's the term coming out from this term here. Whereas here, when we factor out the minus lambda squared, we're going to get 2 of them, right? And we can then factor out lambda squared one more time. And then we will have minus lambda squared times lambda squared plus 2. Did I mix the sign again? Well, if I'm factoring out minus lambda squared, then it should be lambda squared plus 2, and then plus another 2. So then that's going to give us 0. And of course, what we get in the end is lambda. I can remove the -1 because I can multiply both sides by -1. So what I get in the end is lambda squared times lambda squared plus 4 equals 0. A very simple equation that can be solved immediately, right? So what are the eigenvalues? Lambda 1 equals 0, lambda 2 equals 0, lambda 3 equals to 2, and lambda 4 equals to 2 as well. No, sorry, lambda 4 equals to -2. So there are there are 3 technically eigenvalues, but one of them is repeated. But remember, we need 4 of them in the diagonal matrix. If I go back here, the diagonal matrix needs to have same dimension as A. So there needs to be 4 entries in there. And because we only get 3 eigenvalues, and we want the eigenvectors to be linearly independent, we know that we cannot get linearly independent eigenvectors across different eigenvalues, since eigenvectors for different values is going to be... No, wait, what am I talking about? Right, so I realized that something that I wanted to say is beyond the theory that we covered. So I'm not going to go into that, except instead we're going to get the eigenvectors out. We're going to I'm going to say what I was going to say then, and namely what will be apparent there is that the eigenvalues that were not repeated roots for the characteristic equation will only give rise to one-dimensional eigenspaces, so there will be at most one eigenvector for each eigenvalue. And on the other hand, the eigenvalues that are repeated can potentially give rise to several linearly independent eigenvectors. We need altogether 4 eigenvectors, and we had 3 eigenvalues. So there was a problem of how to get 4 eigenvectors out of 3 eigenvalues. Which of the eigenvalues is going to contribute in terms of 2 eigenvectors? But since we want them to be linearly independent, we want the dimension of the eigenspace to be more than 1 for that eigenvalue. But we never discussed in the theory how the dimension of the eigenspace relates with the repetition of the multiplicity of the eigenvalue as a solution of the characteristic equation. On the other hand, it is definitely not the case that always when you have a repeated root for the characteristic equation, you will be able to get as many linearly independent eigenvectors for that eigenvalue as the number of repetitions. But for diagonalizable matrices, the idea is that for diagonalizable matrices, we should be able to do that. But that's something that subtle detail we didn't cover in the theory. It's beyond the material we're having look at in these videos. And so, but we don't really need that for the practical problems, because in each case we will be able to find those eigenvectors by observing what the dimensions of the eigenspaces are. So the final solution we will get in terms of the eigenspaces is going to suggest to us which of the eigenvalues is going to contribute with more than one eigenvector, and then we will see then that it will be exactly the eigenvalue 0 because of the repetition as a root of the characteristic equation being more than 1. Okay, so at this point then, in agreement with the theory background we have, let us not think of these as 4 eigenvalues, but rather let us think of this as 3 eigenvalues. And so I'm going to delete one of them and then reindex them. So we have 3 eigenvalues. Lambda 1 equals 0, lambda 2 equals to 2, and lambda 3 equals to -2. And now for each of these eigenvalues, we want to find the eigenvectors. And that, as you know, is quite an elaborate task. We need to solve system of equations in each case, so let's do that. We copy down this matrix. I'll try to be a bit quick, even though I should also try to make sure that I'm not going to make a mistake. So lambda 1 equals 0. Let's see what system of equations we get for that. By putting this value into the matrix, we're going to get 0, 1, 0, 1, 1, 0, 1, 0, 0, 1, 0, 1, 1, 0, 1, 0. And now there is some repetitions in the rows, as you see. So we can remove the repeated rows, in other words, replace them with 0 rows. So we'll have 0, 1, 0, 1, then 1, 0, 1, 0, and then we have 2 rows of 0, right? And so what is this going to give in terms of the eigenvectors? Well, before we proceed with anything, we perhaps first want to get this into the triangular form, and so we just can achieve this by swapping around the first and the second row. And so we get this. And then the method there is to look at the diagonal. And so because the last entry here is 0, remember this is now the last line here is the equation 0 times k1, 0 times k2, 0 times k3, 0 times k4 equals 0. And so it doesn't give any restriction on k1, k2, k3, or k4. But the more canonical way of interpreting this matrix is to go from to go upwards along the diagonal, and when we encounter a 0 in the first case, so in the case of the bottom row, we then know that the last entry in the eigenvector can be any real number except 0, of course. Well, except 0, not quite true, because there might be several parameters then that don't all have to be non-zero, right? So the eigenvector there for lambda 1 eigenvalue will have some k here. What about the second from the bottom, the second entry from the bottom? Well, that's read off from this second from the bottom in the diagonal of the extended matrix, and that's 0 again, so that gives another parameter. And so we have these parameters now, s and k. And we now want to figure out the first and the second entry. We again go from bottom up. So for the second entry, you see here that the last one was, the last entry is k there, and there's a coefficient 1 here, and this second entry also has 1. So we bring this over on the other side of the single equation we get out of the second row, and we'll see that the second entry here is minus the fourth entry. So we'll have here minus k. And what about the first entry? Well, the first one is minus the third one, so we'll have minus s there. So this is the eigenvector in its general form. Of course, we can't have both s and k to be 0, but one of them can be 0. And as predicted, you see we get 2 parameters, and that's suggestive that the eigenspace is going to have dimension 2. And to see this more clearly, we can pick out 2 eigenvectors that span all of these ones. So how are we going to do that? By selecting the s's and k's to be 1 and 0. So what we want here is to represent this form as a linear combination of 2 linearly independent eigenvectors, and that can be done by putting here s, taking s to be 1 and k to be 0 is going to give us minus 1, 0, 1, 0. And then taking s to be 0 and k to be 1 is going to give us 0, minus 1, 0, 1. And you can check now that the sum of these two is indeed that one, right? We got minus s here plus 0 times k, which is minus s, and s times 0, which is 0, plus minus 1 times k, which is minus k, and so on. Okay, now these two vectors, these two, are linearly independent. How can I see this? Well, the second one is not a scalar multiple of the first one, and that's what it means to be linearly independent, right? In the case of two vectors, and none of them also should be zero vector. So the linearly independent eigenvectors we can get out from the eigenvalue lambda 0, and we need as much as possible because we want 4 linearly independent eigenvectors. So we're not going to just pick one eigenvector here, since we can afford to pick 2 that's going to be linearly independent, and the 2 we'll pick will be these 2. So we will have our k k1 to be, I don't want to call this k1, k1 to be minus 1, 0, 1, 0, and maybe k1, 1, and then k1, 2 to be 0, minus 1, 0, 1. So both of these now correspond to the eigenvalue lambda 1 equals 0. And let's mark it so we remember what we got here. Okay, great. Now we need to chase for eigenvectors for the other eigenvalues. And we follow the same process. We take this extended matrix and we put in there the corresponding value of lambda. So lambda, lambda 2 was equal to 2. So we're going to put this there, lambda 2 equals to 2. And then this is going to give us minus 2, 1, 0, 1, 0, 1, minus 2, 1, 0, 0, 1, minus 2, 1. And then 1, 0, 1, minus 2, 0. And now we do the row operations to simplify this and bring it into the row echelon form. So let us multiply the second row by 2 and add to the first one and put that in the place of the second row. So here we keep minus 2, 1, 0, 1. And then we're going to put 0 here because 2 times 1 plus minus 2 is 0. Then 2 times minus 2 is minus 4 plus 1 is minus 3. 2 times 1 plus 0 is 2. And then here we have 1, right? The third row we can keep the same way. And the fourth row, let's do the similar thing here. Multiply the fourth row by 2 and replace that with the first row added to that fourth row multiplied by 2. So we'll have a 0 there. Then if we add these, we'll get a 1 here. Then we'll have a 2 there. And then we'll have, so that's going to be minus 4 plus 1 is going to be minus 3, right? Okay, this requires more row operations. I might not be taking the shortest route here. Maybe you can do this better than I. So then I would subtract I would keep the third row. Wait a second. First I want to get rid of I want to put the 0 there, right? So I'm going to, well, many ways we can do this, but let's do it in a more canonical way. So I'm going to multiply the third row by 3 and then add to the first one. So that's going to give us 0 here. This is going to be minus 6 plus 2 is minus 4. And then 3 plus 1 is 4. And the same for the last one. Multiply that by 3 and add to the second row. So it's going to have a 0 there. And then 6 plus 2 is 8. And then minus 9 plus 1 is minus 8. Right? All right. Now we have minus 2, 1, 0, 1, 0, 0, minus 3, 2, 1, 0. Then we have 0, 0, minus 4, 4, 0. And here we can multiply the third row by 2 and then add to the fourth row and replace the fourth row with that. So we'll have 0, 0, 0. So 2 times 4, yeah, we actually get a row of zeros, right? Because the fourth row is the same as the second row, third row multiplied by minus 2. Great. So what can we read off from this extended matrix? Well, this is now for the K2, right? It is clearly the case of a one-dimensional eigenspace. The only free parameter here will be the fourth one, and all the others are going to be expressed in terms of that, right? So maybe I'm not going to call this K2 yet. I'm first going to keep it in the general form. So the last parameter there is some K. By the way, I shouldn't think that this K is the same K as the other one. In both cases, K can be arbitrary number, right? And then the third one is going to be minus K. Sorry, no, it's K again. Right? Now, what about here? So we have to put 2K, then it's 1K, and bring it on the other side, and so it's minus 3 there, and so we've got minus 3 on the other side as well, so it's K again. Okay, what about putting this here? So we'll have a K, and on the other side it's also K. Wow, everything is a K. It's quite beautiful, isn't it? So then, well, K isn't 0, because otherwise 0 vector cannot be eigenvector. So we can then pick the K2 to be one of these, which we can pick to be a column of ones. Of course, any other value there would also work. We just want to take the simplest possible one. And for me, number 1 is simpler than any other number, as soon as I'm not allowed to use number 0. Otherwise, I would have wanted to put number 0 there, which is definitely simpler than number 1. Okay, so we got now the second eigenvector, well, actually the third one, because we generated 2 eigenvectors out of 1 eigenvalue. So we got 1 eigenvector out of the eigenvalue lambda equals to 2. There's no way we can get another one, because any other one will be a scalar multiple of K2, hence the sequence of eigenvectors will not be linearly independent. And the next step now is to take the eigenvalue lambda 3 equals to, what was the other eigenvalue? It was equal to minus 2. And then we do the same thing. By the way, I hope when you're watching this video, you're fast forwarding it, all my calculations, not only because sometimes I make mistakes, but also because I don't think it's very good idea to observe calculations which are quite straightforward for you. But of course, if you're not sure about certain calculation, then you don't want to fast forward that. I'm still keeping all the calculations here for the purpose that maybe you're not sure about something, and just to make it more clear how we're getting all these numbers out. I do apologize for the mistakes I make every now and then, but I also do believe that by you observing my mistakes and noticing that they are mistakes, of course, which is what I'm hoping that you're doing when I make a mistake, that this way you learn better, and also you learn that it's okay to make mistakes, except that unfortunately it is not okay to make mistakes in the exam. That's why I don't like exams, to be honest. Anyhow, so that's the extended matrix. Now we want to solve for it, but before we do it, we want to do again the row operations, right? and I'm wondering if I should be more clever this time. So maybe I'm going to just subtract the, well, I mean, I have to then keep the first one, second row. No, let me still be more canonical there. So multiply by -2 and then add, and we'll have 0. -2 times 2 is -4, adding -3, -2, 1, right? Then we have here we have 0, 1, 2, 1, 0, and then multiply again by -2 and add 1 there, then -2, and adding this gives 3. No, I made a mistake there. By -2, it's going to -4. -4 plus 1 is -3, right? Okay. Now we simplify this further. So we'll have 0, -3, -2, 1 here, and then let's multiply the second row by the third row, sorry, by 3 and add to the second one and replace the third one with that. So then we'll have 0, 0 here. 3 times 2 is 6, and that added with -2 is going to be 4. And 3 times 1 is 3, and that added to 1 is going to be 4 as well. In the last one, we'll do the same row operation. So then we'll have -6, -2 is -8, and then what did I say I was multiplying by? 3, right? So then we'll have -9, and plus 1 is -8. And of course, now we see that the last row is again a multiple of the third row. So we're going to replace the last row with a row of zeros. There we got all these numbers. Now we have a row of zeros here. And now let's start creating the solution of this. So once again, because of that 0 there, remember we want to, a quick way of this is just to go up along the diagonal. So the last one here gives us a free parameter k, and then here we have -k, right? The third entry is -k because force goes away, and bring it on the other side, and you get -9 there and all of that. Okay, now putting -k here is going to give us 2k, and a k there is going to give us 3k, and putting on the other side gives us k, right? And I guess this will be -k. Let's see. The second one is k, the last one is k, so it's 2k, 2, bringing, 2 something, and bringing that on the other side, it's going to give us -k indeed. And of course, we don't want k to be 0, and we again, we have a case of one parameter, which definitely means the eigenspace is one-dimensional, and we want to pick that, therefore we can only pick one eigenvector from there to keep the sequence linearly independent, and what we'll pick is 1, -1, 1, -1, 1. Okay, so at this point, what we did is to make is to find eigenvectors and also to find the eigenvalues. And so we are already able to diagonalize the matrix, because that's all we need for diagonalization. We need linearly independent eigenvectors and eigenvalues. But remember, our initial goal was to orthogonally diagonalize the matrix. So we don't want to have just linearly independent eigenvectors. We want to have more than that. And namely, we want to have the eigenvectors to be orthonormal, the sequence of them to be orthonormal. So let me just collect all the information. So the eigenvalues were 0, 2, and -2. So let's write them here. Lambda 1 equals 0, lambda 2 equals to 2, and lambda 3 equals -2. And the eigenvectors for these were, so for lambda equals 0, we had these one, -1, 0, 1, 0, and 0, -1, maybe I just copy that. So this is the 2 we had for that value of for that eigenvalue. On the other hand, sorry, that was too small, I think. On the other hand, for lambda equal to 2, the eigenvalue, as far as I remember, was 1, 1, 1, 1. Okay, so K2 is 1, 1, 1, 1. Let's just double check that. Indeed, that's so. And then for the eigenvalue minus 2, we have K3 is minus 1, 1, minus 1, 1. Now, if I just wanted an ordinary diagonalization, what would I do? Not an orthogonal one. So if I wanted an ordinary one, I would take my diagonal matrix to be matrix consisting of the eigenvalues, and the matrix P to be consisting of the eigenvectors. And remember how they should correspond to each other. So the eigenvalues in the ith column of the diagonal matrix should be the eigenvalue for the eigenvector in the ith column of the matrix P. And I want linearly independent eigenvectors because I want P to be an invertible matrix. And so that's how I ended up selecting 2 eigenvectors for that eigenvalue lambda equals 0. And now I need to start putting these, but now since these 2 eigenvectors come from the same eigenvalue, that eigenvalue will have to appear twice in the diagonal matrix. And then that's when you see that the number of times it appears there is exactly the characteristic, sorry, is exactly the multiplicity of the solution of the characteristic equation. So once you solve the characteristic equation, you count multiplicities there. Already that's suggestive to you how many eigenvectors you will be picking out for that eigenvalue to be placed in the matrix P. Okay, so we're going to place them in this order, 0 twice, and then 2 and minus 2. 0, 0, 2, minus 2. And so that's our diagonal matrix. Now, the eigenvectors have to be placed in the corresponding order. In terms of K11 and K12, the order doesn't matter, because all we need the order for is that the correspondence with the eigenvalues is preserved. But both eigenvalues are the same. So the order between K11 and K12 doesn't matter. And so we could pick, for instance, this order. And for K2 and K3, we are forced to use the order in which the corresponding eigenvalues appear, and so that will be 1, 1, 1, 1, 1, and minus 1, 1, minus 1, 1. You see, we had a choice here how to put the order of eigenvalues, and that would have determined the choice of P. And then that's, you see there clearly that there are multiple answers to this question, up to rearrangement of the columns of D and P. But for each answer, the columns of D should match with the columns of P in the sense that the eigenvalues should match with the corresponding eigenvectors. Okay, great. Now, in orthogonal diagonalization, we want the matrix P to be orthogonal. And that means that the columns should be, first of all, they should each have norm 1. The length of those vectors should be 1. And secondly, every 2 of them needs to be orthogonal to each other. Now, because we don't have much choice with eigenvectors that come from different eigenvalues, it actually turns out that if they do come from different eigenvalues, they will automatically be orthogonal to each other. And we don't even have to check that. But if you want to check that, you can. Look, for example, if you take the inner product of K to K3, you'll have 1 times minus 1, 1 times 1, 1 times minus 1, 1 times 1. You add all of these, you get 0, right? So in the same way, K2 will be orthogonal to K11, it will be orthogonal to K12. Why? Because 2 eigenvectors for different eigenvalues are always orthogonal to each other. In the case when we are working with eigenvectors, of course, of a symmetric matrix, which does admit orthogonal diagonalization. And remember, symmetric matrices are exactly the ones that admit orthogonal diagonalization. But for those eigenvalues for those eigenvectors that came from the same eigenvalue, they don't necessarily need to be orthogonal to each other. We want them to be orthogonal, so we have to fix it up if they're not. And so if I visualize this, what's going on here is that the 2 eigenvectors are giving me a certain plane. They're spanning a certain plane, this eigenspace for lambda equals 0. And what we want in this plane, we want representatives of two vectors that are orthogonal. So if they're not, I want to fix up one of them and get another one that will be orthogonal to the first one. And there are methods for doing this, but in this case, we will not have to do that. Why? Because accidentally they turn out to be orthogonal to each other. Look at this. If you take the, okay, let's now carry it out more properly, the calculation. So let's carry out the calculation for k11 dot inner product with k12. This is the same as the transpose of k11 multiplied by k12. And so it's the same as minus 1, 0, 1, 0 multiplied with 0, minus 1, 0, 1. And you see that this equals 0. And that's what it means for two vectors to be orthogonal algebraically, that this product of these matrices should be 0. Okay, so we were lucky. The way we solved the equation here is the way we expanded this as a linear combination of two linearly independent vectors. It happened so that we were lucky that the eigenvectors we got out of it were already automatically orthogonal. Okay, if they hadn't been, then we would have to adjust one of the vectors as I said before, and there are techniques for doing that. I'm not going to cover this in this video because in this video we don't need that technique. Okay, so once we make sure that everything is orthogonal to each other, which just means making sure within each eigenvalue, because across different eigenvalues the eigenvectors will be orthogonal for free. The next thing is to make sure that the length of these vectors is 1. And how do we make sure of something like that? Well, we take each vector and we stretch it to make the length 1. When you stretch an eigenvector, it will still be an eigenvector, right? Because eigenvectors form an eigenspace, so it's closed under all linear combinations, including stretching. So by stretching these vectors, we're not going to be depriving them from the right of being eigenvector. And another way of thinking about this is that when we selected these eigenvectors, remember we chose suitable values of k in each case, and we just took the simplest ones, but now we actually want to take k's in such a way that the length of this vector ends up being 1. Now, the length of a vector can be computed like this. So let's take the vector k11 and let's compute its length. Another name for it is norm. So what's the norm of k11? It's a generalized Pythagorean theorem that tells us that the norm is square root of the inner product of k11 with itself. So it's going to be minus 1 times minus 1, which is 1, plus 0 times 0, which is 0, plus 1 times 1, which is 1, plus 0 times 0, which is 0. So it's square root of 2. Now, since the length of this vector is square root of 2, if I stretch it by factor 1 over square root of 2, right, then the length of that vector, so 1 over square root of 2 goes out from the norm function, and so the length of that vector will be 1. Imagine inserting 1 over square root of 2 here each time it will be squared, and then factoring it out, you would get 1. Okay, so I mean you would get this principle that the vector goes out of the norm. So to stretch the vector, we just have to multiply each vector by the reciprocal of its norm, and then this means in the case of this vector, it means that we need to divide each of these entries with square root of 2. The non-zero entries, the zero entries will not change. The length of the second vector is again square root of 2, so it's the same result there. Now, what is the length of this vector? This is 1 squared plus 1 squared plus 1 squared plus 1 squared, and square root of the root of that. So it's 4 and square root of 4. And square root of 4, of course, is 1 over 2. Sorry, it's 2, but now we divide by reciprocal of that, and we get this. And I can check now that this vector has length 1 by taking this times this squared plus this squared plus this squared plus this squared and square root of that. So it's going to be 1 over 4 plus 1 over 4 plus 1 over 4 plus 1 over 4. That's 4 over 4, that's 1, and square root of that is 1. And the same here, the length turns out to be 2, and so we have to divide by the reciprocal of the length. So that's how we can adjust the columns of P to turn those eigenvectors into unit vectors. And then we've solved the orthogonal diagonalization problem, because now we've found the matrix P whose columns form an orthonormal sequence because each has length 1 and any two columns in different positions are orthogonal to each other by means of their inner product being 0. And we also have the corresponding diagonal matrix. It was a long discussion because it was a big matrix, but it covered all the aspects of working out orthogonal diagonalization, except the aspect of how to fix up a vector, how to fix up a pair of vectors when they our initial pick is not giving us two things that are orthogonal to each other. But that should be looked at separately, not in this video. Okay, great. So thank you and all the best.